Okay, our second talk is going to be on R-Pingmesh by Kefe Liu, and he's a third-year PhD student at the Beijing University of Posts and Telecommunication, where he's supervised by Professor Zhao Zhang. His research interests include data center networks and network troubleshooting, with a focus on RDMA networks. So, take it away.
Yeah. Thanks for the introduction. Hello, everyone. I'm Kefe Liu, a third-year PhD student at Beijing University of Posts and Telecommunications. Today, I will introduce R-Pingmesh, a service-aware RoCE network monitoring and diagnostic system. Now I will first introduce the characteristics of RoCE network problems. First, commodity RNICs use go-back-N as the transmission mechanism. Therefore, RDMA throughput is sensitive to packet drops. Second, RoCE networks typically require a variety of configurations to ensure a lossless environment. This leads to a high probability of misconfigurations, which can cause packet drops and throughput degradations. Third, RNIC problems are frequent, such as RNIC flapping, which can lead to packet drops and throughput degradation. In addition, distributed machine learning has a barrier effect. In DML, all participating GPU periodically synchronize their local gradients over the network. And the completion time of this process is determined by the slowest GPU. Either RNIC or in-network packet drops can cause throughput degradation of multiple flows, which will further degrade the average throughput of the entire DML cluster. Recently, the size of large language models is increasing, and typical model parameters have now reached 100 billion or even larger than 1,000 billion. To increase the training rate, the DML cluster uses more GPU for training, as well as more RNICs and switches to connect this GPU. And as a result, both the frequency and impact of network problems are increasing. Efficient troubleshooting is critical for optimal training performance. When training fails or training performance degrades, the problem needs to be quickly located. Large clusters that are idle for troubleshooting or running in unhealthy status can result in significant financial losses. However, our existing RoCE network monitoring and diagnostic methods are not efficient. First, we are hard to detect failures and performance bottlenecks when they occur due to the lack of an efficient monitoring system. Second, our existing RoCE network troubleshooting mechanisms could be roughly divided into two steps. Step 1, inspect configurations, logs, and anomalous metrics. Step 2, run benchmark tools in the cluster. This method is time-consuming for large clusters. In addition, when training fails or performance degrades, we are hard to tell if the problem is in the network. One of the most common service failures is nickel communication timeout. This sounds like a network problem. However, the cause could also be a remote process exit due to GPU error, which is not a network problem. Another case is degraded training throughput. The cause seems like a network problem, such as network congestion. However, the root cause may also be bugs in the training code. So the truth is that we often waste time trying to find the root cause of non-network problems in the network. So we need an efficient RoCE network monitoring and diagnostic system. It can quickly detect and locate RoCE network failures and performance bottlenecks. In addition, it can quickly determine if the network is to blame when service performance degrades. When inspired by our TCP networks, Pingmesh is a data center physical and TCP network monitoring and diagnostic system. PingMesh agent has been deployed on most of the servers in our data centers. So if we can extend PingMesh to RoCE networks, we can then build on existing systems with minimal effort. However, deploying PingMesh directly in RoCE networks cannot meet our requirements. In this section, we present our targets and show the limitations of PingMesh. First, we need to detect problems specific to RoCE networks, and we need to use RoCE probes for probing. TCP probes in PingMesh cannot detect all problems in the RoCE queue. Second, the RNIC and switch pack jobs can interfere with each other during troubleshooting. We need to distinguish between RNIC and in-network pack jobs in order to accurately locate RNIC and switch problems. However, PingMesh cannot identify the location of pack jobs. Third, to detect and locate performance bottlenecks, we need to accurately measure the end-host processing delay and the RTT of passes used by the service. However, PingMesh measures RTT at the software layer. Although PingMesh can detect an abnormal increase in RTT when bottlenecks occur, it is difficult to locate them because the increase can come from either end hosts or networks. As shown in the figure, the software RTT measured by PingMesh fluctuates as the host average load changes. Finally, not all detected problems should be resolved immediately. Some problems do not severely affect services. Fixing them may also cause service performance degradation. We need to prioritize each detected problem based on its impact. The priority also helps determine if a service problem is caused by the network. If no P0 or P1 problems are detected when service performance degrades, the network is innocent. However, PingMesh cannot assess the impact of problems on services. Next, we'll introduce the design of R-Pingmesh. Similar to the architecture in PingMesh, R-Pingmesh still has three components: controller, agent, and analyzer. Controller is for ping list generation, and agent is for probing and path tracing. And analyzer is for SLA tracking and troubleshooting. In terms of functions, R-Pingmesh has two independent functions. The first is cluster network monitoring. It constructs RoCE packets to probe between all RNICs in a RoCE cluster. It is service independent and can detect network problems before service run. And the second is service tracing probing. Service tracing probes passes used by services. In this way, it can assess the impact of detected problems on services. Next, we introduce each component of R-Pingmesh. Controller is centralized. It has two core missions. The first mission is to store the latest communication info of each RNIC, including GID and QPN. And the second mission is to create a TOR mesh ping list and inter-TOR ping list for each RNIC in cluster monitoring. TOR mesh is to probe within TOR switches and monitor RNIC status, while inter-TOR probing is to cover all network links between different TOR switches. Agent is deployed on each RoCE server for probing and path tracing. We first introduce how to measure RTT and processing delay in agent. A critical consideration is the choice of qubit type. We compare the features of all three qubit types in the table. In terms of accurate measurements, we need to get 6 timestamps as shown in the figure, and we can then use this listed formula to calculate network RTT and processing delay. Commodity RNIC provides an RNIC timestamp when generating cookie, and all these three qubit types can get timestamps 3 and 5 from received cookies. However, only UC and UD can obtain timestamp 2 and 4. In terms of connection overhead, with RC or UC, the local RNIC must create a QP for each target RNIC, which consumes limited QP context cache in the RNIC. Yeah, with UD, agent only needs to create one QP on each RNIC, which has very low connection overhead. Therefore, agent uses UD for active probing, which can accurately measure RTT and processing delay with low connection overhead. Yeah, sorry. Due to time limits, here we present some probing process highlights. First, timestamp 4 can only be obtained after the first ACK is sent. Therefore, the responder needs to send the second ACK to carry 4-3. Yeah. Second, all duration calculations do not require clock synchronization. The second mission of agent is monitor and probe the fab tuple of service flows. Agent uses eBPF to trace the core to the kernel functions, modify QP, and destroy QP. Yeah, by tracing these two verbs, agent can keep the fab tuple used by services in real time. Then, agent will construct probes with the same fab tuple as the service flows. In this way, these probes can cover the exact network passes used by the service due to ECMP hashing. For path tracing, agent periodically trace through the latest passes of probe packets and their X. This tracing method is easy to deploy. A continuous path tracing allows analyzer to accurately locate network problems immediately as they occur. Yeah. Next, we introduce the data analyzer. Analyzer is for SOA tracking and troubleshooting based on data uploaded by agents. Among all the data uploaded by agent, packet jobs could be attributed to RNICs or switches. And a key task of analyzer is to distinguish between RNIC and in-network jobs. If we can detect anomalous RNICs, we can filter out anomalous probes caused by RNICs and use switch jobs to accurately locate switch network problems. We use TR-mesh to do this. Our experience is to introduce minimal uncertainty. TR-mesh probing involves only 2 links. If a probe from RNIC A to RNIC B shows anomalies, the problem is either at A, B, or the TR switch. If many probes to an RNIC show anomalies at the same time, that RNIC is probably abnormal. Note that the premise for this is that for each RNIC, there should be fragment packet from other RNICs under the same TR switch, and Pingmesh cannot do this. Yeah. The final mission for analyzer is to assess the impact of problems on services. Yeah, if sorry. Yeah. After filtering out RNIC drops, we can get anomalous probes caused only by switches. Then analyzer can use a simple voting algorithm to infer abnormal devices. It traverses the passes of these probes and their X, and counts the number of times each link or switch is traversed. Yeah. The link or switch with the highest number of votes is the most suspicious. Yeah. And the final mission for analyzer is to assess the impact of problems on services. Yeah. If a problem is detected by service tracing, this problem can affect the service. Yeah. And if a problem is detected by class monitoring but not by service tracing, this problem is outside the service network. Note that if service performance degrades, but service tracing does not find any problem, then the service network is innocent. Yeah. Next, we will show the performance of R-Pingmesh. Yeah, we have deployed R-Pingmesh for over 6 months on tens of thousands of RNICs. Yeah, we evaluate R-Pingmesh in large DRML RoCE clusters. Yeah. As shown in the up figure, during checkpoints, the RoCE network is briefly idle. In addition, there are 2 anomalous throughput degradations. And at the same time, the network RTT measured by service tracing also decreases due to less congestion. This shows that R-Pingmesh can accurately measure latency metrics and use them to reflect service status. For the 2 anomalous throughput degradations, service tracing quickly detects 2 severe packet drops on switches, which confirms that both degradations are caused by packet drops in the service network. In addition, during this time, cluster monitoring detects an anomalous RNIC that continues to drop packets. However, service tracing does not see any RNIC drops. Therefore, we conclude that the problem is outside the service network. Yeah. In another case, the service training rate and average throughput continues to decrease, and our service team suspects that the network is congested. We then check the metrics in R-Pingmesh. As shown in the figure, the RTT is also decreasing and the processing delay is stable, proving that there is no bottleneck in network or CPU processing. As shown in the table, during deployment, R-Pingmesh effectively detect and locate 14 types of problems caused by hardware failures, misconfigurations, network congestion, and intra-host bottlenecks. Yeah. Next, we present some of learned experiences. Yeah. First, we can use the measured tail RTT to reflect network congestion. Our DML services typically use two communication modes, all-reduce and all-to-all. From the network latency measured by R-Pingmesh, we can see that all-reduce is less congested, and all-to-all can cause severe congestion. And compared with DCQCN, our self-developed congestion control algorithm can effectively reduce the tail RTT in all-to-all. From the network congestion detected by R-Pingmesh, two causes are the most common. The first is TOR switch downlink congestion caused by MAN2 incast, which should be alleviated by tuning congestion control parameters or design better congestion control algorithms. And the second is TOR switch uplink congestion caused by ECMP hash collision, which can be avoided or mitigated by designing better load balancing algorithms. And the framework of R-Pingmesh ensures that it can adapt to any network topology. In practice, we can leverage the feature of network topology to improve the system design. For example, in real optimized networks, probes between RNICs on a host traverse the top tier switches in the cluster. Therefore, we can have RNICs on a host probe each other to cover all network links. And in this way, agent does not need to rely on controller to get ping lists. Furthermore, agent can detect one-way timeout and measure one-way delay. With one-way probe data, we can locate network problems more accurately. Yeah. So in conclusion, we propose R-Pingmesh, a RoCE network monitoring and diagnostic system. R-Pingmesh can be easily deployed with low overhead. And it can detect and locate failures and bottlenecks in networks and end hosts. In addition, it can determine if a problem is in network and assess its impact on services. Okay, thank you. That's all for my presence today. Yeah, thank you very much. Yeah.
Questions?
Hi, thanks for the talk. Srikanth from Meta. So you mentioned in your, I think, one of your last slides that for rail optimized topologies, you can measure one-way delay.
Yeah.
Can you expand on that a little bit? Thanks.
Yeah, this slide.
Yeah, so you mentioned you can measure one-way delay.
Yeah.
Can you explain how?
This is because you can probe, as shown in the figure and with the red line, you can use RNIC1 to probe RNIC2. And the two RNIC are on the same host, and so there is no need to send the ACK from the RNIC2 to RNIC1. Yeah. So we can take a timestamp in RNIC1 and take a timestamp when it sends the probe, and take a timestamp in RNIC2 when it receives the probe. And this is a one-way delay. Yeah.
One of the things that you asked about, proposed, was to change the 5-tuple in order to get like signal from all the possible network paths,
yeah.
Right? So is it fair that if you use something like flowlets, if you're instead of ECMP, then this scheme won't work, right? Because it depends on how the flowlet routes the probes.
Yeah, you mean if you use flowlet and
Load balancing.
And change 5 tuples, it cannot cover all the links?
Right, right.
Okay. And I think I think in our probing method, we use small packets, and the small packets is only less than 1K, yeah, 1 kilo, yeah. So I think for each packet, it will be hashed to different passes.
Right.
Yeah. And for each packet, we will change the each probe packet will change the 5 tuple. Yeah.
Right.
So I think it will not be determined by the flow rate. Yeah.
Oh,
Okay. Setting. Yeah.
I see.
Yeah. Yeah.
All right, well, let's thank the speaker one more time.
Thank you.